Welcome to Zephyr-friendly embedded display shopping guide. In this talk, I want to give you a beginner's guide to embedded display to the specific terminology so that you can choose the best suited one for your application. But also I want to give a sense of what changes in your electronics design process if you decide to take software into account right from the beginning, which I strongly advise you to do. But before we start, let's have a word about me. So I'm Eve. I have a background in electronics engineering. I've worked for 10 years in consumer electronics, mostly small and medium-sized companies. I have been doing electronic design, software integration, debugging, testing. I have been using Zephyr for around 3 years professionally, mostly for measurement and test automation, and also for side projects and learning purposes. I have a pet project. I have a custom board design and I wanted a display for it. So it was my first time going shopping for one of those. First, I had some requirements. I did want to be compatible with Zephyr out of the box, no driver writing involved. And I did not want a ready-made shield. I wanted a display that's on catalogs, more with a FPC connector. So I started looking for my perfect product, and that's where I got completely lost with the references and the different texts, and that's why I wanted to make a guide in order to make sense of all of I learned during this process. Okay, so we will start by a very broad definition of what should the display do and how to choose a type of display. Then we will move on to the physics section, where I will explain all the different technologies for displays. And then we'll talk about the controller. It's a bit more on the electronics side, and about the different interfaces. Okay, so first we make a sort of distinction between two broad categories of displays. The first one is the obvious one we think about when you talk about displays, the kind that has a pixel matrix. So you have an array with pixel and colors. It's a straightforward display. And you have the other ones, the other section that contains all the miscellaneous things, mostly alphanumeric things. So you have the alphanumeric LCDs, and also the segment LCD and LED, something called 40 segment, that's like 7 segments, but for displaying more characters. And it's kind of look old school, but they're still everywhere if you look around you in electrical appliances, measurement systems, and a lot of devices uses them still. So for the pixel matrix type, we have an issue that they require a lot of code and memory, and they are complicated to integrate. It's not a painless experience exactly. So actually having ready-made software really changes the way you consider this type of display. So we have a display driver API in Zephyr. It's quite easy to understand. You have a display write function, you give it X and Y and a buffer of pixels, and it just converts it through the driver. It converts it to the bunch of hexadecimal data you want to pass on to your bus to draw the pixels. So it's quite easy. And you have a bunch of drivers that will help you do this translation from the abstracted coordinate plus color format to the actual binary that happens in the bus. And you also have another driver API for the displays that are alphanumeric this time. Typically, the alphanumeric LCD displays, they have this ROM with characters that are indexed, and on the bus you won't see any indication of what the pixel does. The module is handling it itself, and you will be just sending an index, and the driver API will take as input a text this time, not a coordinate and color. But of course, you can also convert a character to pixel matrix and then send it to a standard driver to a pixel matrix display. And that's the goal of the CFB library. It's a library that helps you convert a character directly to pixel matrix and then use the driver, like before, to sending to the display module. So it really helps with the process of displaying characters. And you might know that one, but if you want to handle very advanced graphics, you have the LVGL library that converts, that actually takes higher level objects like buttons and transparency and text areas and colors, and it will convert it the same like a soup of pixel and sending through the driver to the display module. So there's the last category of displays that we call smart display, and actually what they kind of do is take advanced graphics library, kind of like LVGL, and have them embedded into the display module. So you don't talk to your display with all the pixels, you just give them an advanced command like draw me a transparent button or something, and the coprocessor that's inside the module will handle all the processing and make it on the display. And you have start of a driver in Zephyr for this type of display in MISC, and it's only for FTDI 8 series of coprocessing for display. Okay, so that makes a very interesting choice with lots of different options. Of course, before using Zephyr, I would have gone for the alphanumeric type of display because, well, I didn't need lots of advanced graphics. I could tolerate the look of an alphanumeric old school display, and I absolutely have no resource and development time to handle the integration of a full beautiful pixel matrix display. But that changes with software, because now I have a ready-made library and drivers that can help me handle this complexity. And so, well, I decided to go for CFB and pixel matrix instead of integrated LED, LCD, alphanumeric LCD product. So now it's time to explain all the crazy acronyms that you can find in catalogs. Sorry for that. Yeah, let's go. Okay, so 3 broad categories of displays. The first one is LCD, the second e-paper, and the third is LED and OLED type of display. Okay, so LCD is a complicated category because you can find in this category both the old school look. You have your Fluke display multimeter, you have your Nokia 3310 type of matrix display, and you can have in this same LCD category the very advanced type of display that you can find on your smartphones. And they are all LCD display. So we tend to name them with historical reasons. LCD and TN and STN will refer to the classic look, and TFT IPS to the more advanced type of display. I'll explain why. Well, so first LCD, it's a very interesting tech. You have pixels that are made of a kind of GUI that can change its polarization with an electrical field. And so you apply a voltage, and it changes the transparency of your pixel. And the good thing with it is that you have analog control. You can put it to 50% transparency. It always requires a backlight. It just changes the transparency. That's why you have sort of weird naming convention. If you see RGB LCD, sometimes it's the LED that's RGB, not the pixel itself. Can be sort of tricky. So yeah, LCD requires a backlight. And for additional fun, you have several types of LCD pixels. You have something that was invented first in the 70s, that's TN, meaning twisted pneumatics. And by default, it's transparent. And more recently, you have a technology that's called IPS. You change the type of, the way you use the LCD GUI. And by default, this one is opaque. So IPS is more recent. It's an important thing to note. So now what is TFT? we do the entire list. What is TFT? TFT answers the problem that you need to miniaturize your pixels. So you need each pixel to have a tiny electrical field in order to control your LCD. And silicon wafers don't help you because they are completely opaque, so light from the backlight cannot get through. So the solution here is to have a technology that can deposit transistors directly on glass. They're really tiny. And we also have something that's called ITO, which is a transparent conductor, used everywhere. The only issue is that indium is pretty rare and might run out. We don't know when. And if you mix this technology, TFT transistors and ITO capacitors, you get something we call a TFT backplane that you can use to control tiny electrical fields to make the pixels from the display. So that's what TFT means. So back to first slide, finally. So LCD, when you see it alone in catalogs, generally you might think it refers to the classic TN LCD display. Same thing if you see TN or STN or every variant of TN technology that they invented. It mostly refers to classic TN LCD display. TFT refers to TFT TN LCD displays. And IPS tend to refer to TFT IPS LCDs. So a bit confusing, but it's kind of historical reasons for this naming more than proper logic. Okay, a quick word about e-papers. They're quite simple to understand once you get the TFT plane concept, because they use a TFT backplane too. Instead of having a pixel made of LCD, you have a pixel made of charged ink, and you can switch the side of your charged inks thanks to an electrical field. And the good thing is that it stays that way once you remove the electrical field, so you can turn off your power supply and your image is still displayed. Weirdly, it exists in 3 pigments. I don't know how it works, but yeah, it works. Only monochrome are supported now by Zephyr. And you can find all types of different names, like ESL for electronic shelf label, because they are used mostly in the supermarkets for prices display. And you find EPD, that's electrophoretic or electronic paper, never know. And you have e-ink, which is trademark. So now, last section is LED and OLED. So LED, you know, you put LED and you make them in a matrix, and it makes a display. And the OLED is actually miniaturization of this concept. In order to miniaturize, you will make it vertical, actually. Instead of having your junction that's horizontal, you make it vertical. So one side has to be transparent in order for light to escape. And the O refers to the sandwich layer in the middle that helps producing light. So contrary to LCDs, they produce their own light, the OLED displays. And then you make your cathode and anode in a grid pattern so that each intersection actually makes a tiny LED. And that's how you have a miniaturized display. Well, they're quite interesting to control because LED have only 2 pins, so you can only update one single row at a time and need refreshing by rolling through all the rows. You know, the pixel will hold state only for a little while until the next refresh. Okay, but of course, if you need to be refreshed more frequently and you have a higher range display, what do you do? You add a TFT backplane to your passive matrix display, and that's how you make higher range OLED displays. Is that they're actually OLED plus some kind of TFT backplane. And the distinction is that the passive matrix that we saw before with update row by row is called PM OLED, and the ones with the TFT backplane are not called TFT OLED, but they are called AMOLED. And they're generally higher range, with more colors. and a surprise category included just for fun. They're mostly legacy. It's VFT displays, meaning vacuum fluorescent displays. They work exactly like neon gas. You light up a pixel with gas and voltage, and you still find some drivers in Zephyr for this, and you can find them on websites. And they were very in fashion for old CD players, so they make for good, probably for good upcycling projects. Okay, so that's for the cheat sheet. As a recap, you see LCD, weird naming stuff. LCD and TN are more refer to the classic TN LCDs, TFT and IPS to the advanced LCDs with lots of colors. Everything starting with probably an e-paper display. AMOLED is a big OLED range. PMOLED rather small and monochrome types. And VFD is the thing with 80s neon look. Finally. So we move on to explaining what's a display controller, answering the question, now that we have a display panel, how do we control it with our good old MCU? Well, we sort of cannot control it with our good old MCU because first we have lots of pins for all those pixels, and you probably need to have a memory in order to remember what pixels to refresh, and they probably need analog control too. So instead of making MCU capable of that, we use another IC that's called a display controller. It's a specialized chip to drive display panels, and its peculiarity is that it's built mostly built directly inside display modules. So for you, it will be quite transparent, but it's there. There's a chip here. And so what you find in catalogs is not just display panels, it's an assembly of a display controller plus a panel plus mechanical parts. And those products tend to be tailored and manufactured in small runs. Okay, so I included a picture of what they look like. They do not look like your usual chip that you can buy on DigiKey. They're actually not even put in a plastic package, and so the silicone in this case is soldered directly onto the glass, and we had a bit of glue or I don't know what, and this technology is called chip on glass. So that's why you can find the display references easily on distributors. It's soldered directly onto glass. You cannot play with it for in your DIY projects. Okay, so on this slide, you have a range of modules that all have the same display controllers inside, embedded. On the top row, you can see modules with FPC connectors for your custom board projects, and the bottom row is more for makers with nice header connectors. And you can notice that they have different sizes, they have different connectors, they have different mechanical parts. But that share the same display controller, and they will share like 99% of the code that's used to drive them. So in Zephyr, the drivers will actually refer to the controllers only, which is described in the controller datasheet. And if you're looking for your module specifics, like the size and the offsets and the orientations, you will find them in the device tree properties, and they will correspond to what's described in your module datasheet. That's different from your controller datasheet. The module datasheet will mostly have only those information, mechanical informations, and a reference to the controller the module uses. Well, those data, they are either if your product is a shield, you can find some shield device tree overlays that describe exactly what your shield does and already has all the right values on the shield. But for displays that are more custom, they are put directly into the board device tree, which can be a bit tricky to understand because in that case, they are not parameters from the board directly, they are parameters from the module, so you cannot play with them or use them for rotation or whatever. They correspond to an internal cabling of the module, so probably use what you found in the datasheet and just don't touch it. Okay, so I tried to list all the controllers I found in tree recently. Inox Display API first. It doesn't look very impressive, but actually a lot of ground is covered by only the first one. The Hitachi 4478. It's an alphanumeric LCD display that's used basically everywhere in modules. And you also have a nice 7-segment GPIO driver for fun. Okay, and that's about what I could find in the display API. Lots of interesting things. You can see the TN-LCD section refers to the LCD that are not TFT but dot matrix, the one with the greenish look from all the phones. I also tried to mention which ones are packaged and which one are COG. So what I found is the only one package is the one for to make LED matrix. If you want to make a big LED matrix on a custom board, this is probably your component of choice. So finally, there are some tricky things to know about how the display modules and MCU are connected. So there are two ingredients, the interface on which you talk to. Most of the time, if it's SPI and I2C, you don't have to worry if your MCU supports it or not, but if it's something more advanced like DSI or RGB protocol, maybe you should start looking into your MCU datasheet to see if you have support for that. And you have the controller driver, the one implementing the custom protocols the display uses to be addressed to. So there are not support for 100% of interfaces on 100% of controller drivers. That would be a little bit crazy. Zephyr made some choices that are pretty reasonable to support mostly SPI and I2C, and the MCU parallel interfaces tend not to be really popular. So you have an example of the Elitech 9341 controller that could theoretically support older MCU parallel protocols, but they are not implemented into this driver yet, if you want to do it. Okay, so if you don't have a lot of animation or resolutions, if you have a reasonable display project, the serial interfaces are really the most common and easier to use, easier to debug. You have some displays that work with I2C, a really tiny one, and others with SPI flavors that are also renamed MIPI-DBI type C. So C is important. With a 3 wires version that corresponds to normal SPI, because apparently MISO doesn't count in this context. And the 4 wires version which is like a SPI but with a data command line switch. So that's an example of architecture, which I found pretty cool because it's the one I did. You have a ST microcontroller, and I'm using the SPI port to talk to my small display. And on this, so I have the example commands from the controller, and it's sending just a bunch of binary commands like AE is setting it off, AF setting it on. And so it's a pretty common architecture. Okay, so what if you need something more powerful? one solution that's usual to use is to use a LCB RGB interface. It's only for LCD display first, TFT. And it's an older interface that allows to communicate to your module on a very low level basis. In this type of interface, you will send to your display all the refresh information all the time. You're not stopping the streaming, you're just pushing all the data out there. And you don't need a particular protocol to do that. You just feed data forever. Of course, it requires a hardware block in your microcontroller. It's not every chip that has it. And it's an interesting option for very applications with lots of pixel or video. Since it has many names and there are no convention about how it's named, LCD or TTL or whatever. My trick to recognize it is just to look at the GPIOs that are used. So you look into the datasheet, and if you see H-sync, V-sync, pixel clock, and as many GPIO lines as you need to make parallel color, for instance, if you have 8-bit colors, you need 24 parallel lines plus the 3 clock. So it's 27 lines to be routed on KiCad. Probably a nice hardware implementation to do. And surprisingly, you don't need to use particular protocols. So if you connect your MCU RGB LCD interface to a display, you just put the interface in compatible, and hopefully it will work. So there's something called MCU interfaces that come from maybe older times. Intel 8080 and Motorola 6800 that have a standardized name, MIPI-DBI type B and MIPI-DBI type A. And, well, they exist. And you have a very important interface that's called MIPI-DSI. It's interesting because it has a differential clock and four differential data bus, so it's connector friendly. You can put data on it very fast and very far. And for this application, you need to check that you have the supported MCU peripheral on one side and the supported drivers on the other side. And I know nothing more about it because I didn't read the spec. So, display interfaces, to sum it up, if your life is cool, you just use SPI. And that's what I did. And if you need something with more power, you'll have to really look into the different options to find what best suits your application. So, as a conclusion, so in my scenario, I have a quite simple user interface of a display and something like 3 buttons to make a small menu. It could have been an alphanumeric display. That's what I had in mind at first. But having Zephyr kind of changed my mind, and I went for a PMOLED display instead. It's pretty cheap, it's sold per unit. I can buy it, it's cool. It's small enough to fit on my design. It still has a lot of pixel space. It has a supported controller, yay! And well, my MCU supports SPI, and so that's a perfect fit for me. I hope it helped you choose your display for application too. So that's it for me. So if you have questions, I didn't check the time, I forgot, but yeah. Oh, the display is here. It's tiny, it's cool. Yes?
Do you know anything about touchscreen support? What ports are there that I can have on my display?
Usually, touchscreen support is pretty well separated. It's a I2C peripheral. Usually you have a second FPC that's here, and you can find modules that also have touchscreen support. So you just buy a module with ready-made support. And I think in code they are treated differently, like two devices, but actually in catalogs you just buy them just glued together. But yeah, I hope it answers your question. Yes?
You told about the smart displays which implement some kind of graphics. Oh, you told about the smart displays which implement some kind of graphics acceleration, I would say, inside the display itself. Is there any planned support, or do you work with them in Zephyr, and do you have some comments on them?
There's the start of a driver for the FTDI1, FTDI 80 something. The problem with this in Zephyr is that you have to have a different API for each type of accelerator. It's not standard at all. So you have if you have different ways to draw transparent rectangles for each different manufacturer, then you have to implement a different driver API for each. So I know why Zephyr probably tries to stay away from those, but if you need it for I don't know, if you already have it in your drawers, you will need to go through the process of writing API functions, new API functions for the one you need, actually, the one you need.
And there's no like LVGL backends rendering to those displays, or?
You cannot really do that unless you find a one-to-one similarity conversions. Would be a lot of work. You could, if you want, make a custom module with LVGL inside and invent a new protocol to talk to it. But with a ready-made product, it's probably very, very, very hard. And anyway, you would buy this kind of products. They're really expensive. And you really buy this kind of products if you want to have something fast and maybe unplanned. You just, oh no, I need a display. I don't have any more resources left on my MCU. I can I can buy one of the smart ones.
Thank you. I know some display controllers have support for both a front buffer and a back buffer inside the controller. And to switch between these, do you know if that is supported in Zephyr and the controller drivers?
I have no idea.
Okay.
Sorry.
Thank you.
Okay. If there are no more questions, we can go back to drinking coffee. I also have a smartphone display that I tore down, if you're curious about seeing what it looks like when it's all over the place. So you can ask questions to me later if you need. Yes.